Hi, Assalamualaikum. Good morning. Today we continue on my lecture for CHM477 Inorganic Chemistry. In my previous lecture, I deliberated on Monodentate Ligand, which are ligands having only one donor atom, Bidentate ligands, which are ligands having two donor atoms in a molecule or in ion. And I also went through with you that polydentate ligand, an example of which is ethylene-diamine tetraacetate. Okay, let me just do a little bit of a recap on bidentate ligand, because I realized in my previous video that you could not see some of the items I was pointing to in the video. So let me try and see whether there you are. You could not see that because I did not press the cursor. Anyway, now going back to bidentate ligand, one of the examples of bidentate ligand is ethylene-diamine. Ethylene-diamine is actually ethane diamine. This is the ethane part, and at the end of each carbon you have amine functional group. So you have diamine attached to the two carbons of ethane. Ethylene diamine, sometimes given the short name of EN, has this formula. It has this formula, and when it bonds to a metal center, for example nickel here, this is your nickel, so this is NH2CH2CH2NH2, which is NH2CH2CH2NH2. This is one ethylene diamine bonding to the nickel. Nickel is a transition metal center, to the nickel through one nitrogen donor atom. There is a lone pair of electrons here on the nitrogen. There is another lone pair of electrons here on the other nitrogen. So both the nitrogens bond to nickel in this way. So this is one ethylene diamine bonded to a nickel center. And ethylene diamine is a neutral molecule. It doesn't carry with it any charges. So it doesn't contribute any negative charge to the complex ion that is formed. So there is another second ethylene diamine here, bonded to the nickel in the same manner through nitrogen. See, I am very careful of drawing my nitrogen, which is my donor atom, with the arrow into the nickel, signifying that it is the nitrogen which donates the lone pair of electrons to the metal center so they can share a dative covalent bond between them. And that is the third ethylene diamine. So here actually you have a nickel bonded with three ligands of ethylene diamine. And if you look at the charges, each of these ethylene diamine doesn't carry with it any charge. So this is a zero charge, another zero charge, another zero charge. So the nickel 2 plus that is initially the charge of this metal center is reflected in the overall charge of this complex ion. So whatever is in the square bracket is called complex ion. So the 2 plus charge is reflected as the overall charge of the complex ion. So you have one ethylene diamine, two ethylene diamine, three ethylene diamine, bonding through nitrogen to nickel, another one, nitrogen to nickel, and until 6 times. So you have a 2 chloride, for example. You can have bromide or whatever a negatively charged anion that can counter the charge of this 2 plus, that is actually this charge of the nickel 2 plus has its overall charge reflected here that needs to be neutralized by 2 anions, and in this case is 2 chloride. So that is how a bidentate ligand, ethylenediamine, bond to nickel center, like what I have explained to you here. And sometimes, to simplify the drawing, chemists just do this, making the drawing very clean. Yeah, not too much atoms cluttering the drawing. Oh, by the way, these diagrams are not in your notes that I gave you. I've just added the diagrams, so you please draw them yourself. Make sure you understand that the bonding point is through nitrogen, and sometimes you may see that um, there is just a curved line between the two nitrogens signifying ethylenediamine or En. Sometimes you see that being written. That would be a symbol representation of ethylenediamine. So that is an example of a bidentate ligand, neutral molecule, ethylenediamine bonding to a nickel center. Now let's have a look at another bidentate ligand, which is a charged ion. It is an oxalate ion, sometimes given the symbol of OX, just like ethylenediamine is given the symbol of En. So oxalate is given the symbol of OX, and the formula is C2O4. So oxalate actually comes from oxalic acid. So this is an oxalic acid. Again, this picture is not in your notes, so you can write them down, you can draw them yourself. So this is oxalic acid that had deprotonated, yep, these two hydrogens left, giving you an oxalate ion. So this oxalate ion is totally different in the way that it is not neutral, unlike ethylenediamine. This is a negatively charged ion, yeah, oxalate, because this hydrogen leaves, giving you a negative charge. This hydrogen leaves, giving you another negative charge. So oxalate carries with it a 2 negative charge. Yeah. So when an oxalic or an oxalate bond, excuse me, when an oxalate bond to a metal center, for example, in this case is iron, I put iron 3. I put it iron 3 here because it's going to be relevant to your lab that you're going to be going carry out soon, hopefully carrying out virtually by looking at videos. Okay, so this is iron bonded to 3 oxalate, 1, 2, 3 oxalate. Each oxalate carries with it 2 negative charge, 1 and 2. Another 1 and 2, 1 and 2. So your iron, which is originally iron 3, has a charge of Fe3 plus, and then your ligands 3 oxalate has a charge overall is -6. So 3 minus 6, the overall charge of the complex ion here is 3 minus. So the complex ion with charge of 3 minus has to be balanced out with a counter ion. So this is your counter ion, which is 3 potassium, or it can be 3 sodium, or whatever positively charged main group metals. So you can see here, if your complex ion is positively charged, then your counter ion has to be negatively charged. They have to neutralize, the charges have to neutralize each other. If your complex ion is negatively charged, then your counter ion has to be positively charged, and the charges will cancel one another. So these are two examples of um, bidentate ligand. One is a neutral bidentate ligand of ethylenediamine. Another one is a charged bidentate ionic ligand, which is oxalate. So I hope that is clear about bidentate. If you can still recall from my previous lecture, here I'm talking about monodentate. This is an example of monodentate ligand. So you see here ammonia has a plus, it has a lone pair of electrons on nitrogen. So that lone pair of electrons is donated to your cobalt center, and you have nitrogen bonded to cobalt in this way, monodentate way, one tooth. Yeah, one tooth. So oxalate here, you have this lone pair of this lone pairs of electrons. So one of them is donated to here. The nitrogen, lone pair of electron there, is donated to the nickel here. So each one of the ligands bond to metal centers through donation of lone pairs of electrons on the donor atom of that ligand. Okay, I also went through with you an example of a polydentate ligand in my previous lecture, which I realized when I looked at the video, you could not see my sign, this what I was pointing to. So I am repeating this a little bit so you can do a little bit of a recap. So EDTA is ethylene diamine tetraacetate ion. It has a formula like this, and each one of this oxygen, the one that I have made a circle around them, these were originally OH. So actually it's ethylene diamine tetraacetic molecule, but they lost the OH, lost the proton. One is lost from there, another one is lost from here. Excuse me, it's moving. Okay, another one is lost from here. Another one is lost from here, and another one is lost from there. So you have 4 minus charge. Yep, as indicated. 4 minus charge for your EDTA, and the fifth and the sixth coordination or donor atoms are nitrogen on the backbone of EDTA. So if you want to see how EDTA is bonded to a metal center, you can have a look at this diagram here. That nitrogen over there is this nitrogen. So the lone pair of nitrogen is donated to this lead, which is a metal center, and this nitrogen is bonded to lead. This is the second donor atom. There it is, the second nitrogen, and then the third thing. The third, the fourth, the fifth, and the sixth, and then this is the third. Yep, that is the fourth. Yeah, that one over there. That is the fifth, and that is the sixth donor atom. So as you can see, the EDTA ligand is encapsulating the metal center, making sure that the metal center is wrapped around the EDTA, and you will see that EDTA is a very, very good heavy metal remover. If anybody is getting poisoned by heavy metals, too much heavy metal in the body, So you get some kind of heavy metal poisoning. One of the standard treatment would be the doctors will give you EDTA solution to drink, and the EDTA will bind the metals, and then once it is in this form, it will be easy to be removed as your feces in your natural way of removing bad stuff from your body. So, oops, excuse me. So that is how a polydentate ligand EDTA is used as a scavenging agent, as a scavenger to remove heavy metal from our body if we have too many. Yeah, and EDTA is also used if you look into shampoo bottles or soap bottles. You will see that there is EDTA there, and the use of EDTA in those cosmetics or in the soaps or in the shampoo is to ensure that free radicals are removed from those items to make sure that the shelf life becomes longer. So the soaps or the shampoo can last longer with the EDTA, so it doesn't get bad quickly. Yeah. So that is the recap of my lecture 11. So I'm going to continue with oxidation number of metals in coordination compound. As you can see previously, I did I did tell you that this nickel is 2 plus, this iron is 3 plus. So I'm going to explain to you now how we can calculate the oxidation number of the metal in your coordination compounds. Yeah. Okay, another important property of coordination compounds is the oxidation number of the central metal atom, or it should be ion. If there is a charge, then it should be ion. The net charge of a complex ion, the net charge of a complex ion is the sum of the charges on the central metal and its surrounding ligand. So if you have PtCl6 2 plus ion, this is the complex ion that has 1 platinum uh, and 6 chloride attached to it. Now each chloride carries with it 1 minus charge. Yeah, this cannot be. I am wrong. Each chloride ion has an oxidation number of, oh, this is wrong. This is totally wrong. 1 minus. Please correct your notes, okay? I don't know how these mistakes came about. In PtCl6 2 plus ion, for example, each chloride ion has an oxidation number of 1 minus. So the oxidation number of platinum must be, let me check this. Just 1 second. Okay, just excuse me that I don't understand why my notes were totally wrong. So please, I have made changes. These are the correct note, the correct statement that you should be writing in your notes. Please replace whatever wrong information that I have mistakenly put in the notes that I gave to you. Okay, let's go through this. Okay, in platinum Cl6 4 minus ion, for example, each chloride ion has a charge of -1. So the oxidation number of platinum must be 2 plus, because 2 plus is the platinum. There you are. This is 2 plus. 6 multiplied by -1, -1 for each of the 6 chloride. So that is 4 minus. So how you would determine the oxidation state of your platinum would be like this. If you If you do not know what is the oxidation state of your platinum, then you would say X plus 6 minus 1 equals to 4 minus, so your X must be equal to 2 plus. So 2 plus is your oxidation state of the platinum center. Are you with me? I hope you're with me. So similarly, in the next example, if the ligands do not bear any charge, the oxidation number of the metal is equal to the charge of the complex ion. So in CONH342 plus Cu, this is copper with 4 ammonia 2 plus. Each of the ammonia is neutral, so the oxidation number of copper is 2. How is that? We can try to determine. Again, let's put this y plus 6 times 0 because ammonia is neutral, so you're gonna have y is equal to plus. So your oxidation state of copper, which I put as y here, is 2. So that's how you work out the oxidation state of your metal center. So that is an example that I have given you with how you work it out. So you can have a look at some examples here. You have RuNH3, that means a ruthenium with 5 ammonia and 1 water in the complex ion, and the counter ion is 2 chloride. That's one example, and you are to calculate what is the oxidation state of ruthenium. So the solution, how do you strategize? Just like I explained, it's really very simple. Both ammonia and water are neutral species. Because each chloride ion carries a -1 charge, there are 2 chloride ions, so the oxidation number of ruthenium must be +2. So how do I do that? Let me do this. Insert. Let me try and work this out. Okay. Yep. So you have, if you don't know what is the oxidation state of ruthenium, so for example, you call that X plus 5 times 0. 5 times 0, 0, because ammonia has a 0 charge, plus 1 times 0. Cannot type, okay? Okay, so that is in the square brackets. You can, I just want to show you how the calculation is done. Plus, the Cl is the counter ion, 2 times -1 is equal to, and this whole thing here is a neutral compound, because there is a charge of the complex ion -2, because you know it is -2 because it is chloride, 2 chlorides there. But the whole thing, when you put the chloride in, the whole thing is a 0 charge. So you have, whole thing is 0 charge, so your X is equal to +2. So the oxidation state of your ruthenium in the example above is +2. I hope that is clear. Any question? Ask me later. Yep. X is equal to +2. This is 20. A lot of typo errors. Right. Huh. So that is it. So what about the second, B? I'm just going to go through this with you. So do you know what is the oxidation state of chromium? No, you don't. So you make it X. How many ammonia? You have 6 ammonia. Yep, you have 6 ammonia. So that would be 6 multiplied by 0 charge for each ammonia. And there are no more other ligands. So like that. And how many nitrate is outside is 3. Each one of the nitrate has a -1 charge. So X plus 6 times 0 in the complex ion plus 3 times -1 is equal to 0. So in this case, X is equal to plus 3. So your chromium in that example B at the top there is having a charge of plus 3. Okay, let's go through C. Okay, for example, C, you have FeCO5. This is really very simple. And the whole thing doesn't have any charge with it. And if you want to determine what is the oxidation state of iron, in this case, all you have to do is X plus 5 times 0, because there is no other counter ion there, is equal to 0. So X is equal to, very simple, as X is equal to 0 in the case of C. That means your ion has no charge. Simple as that. That's very simple. And the last example is D, which is, what do you have for D? You have 4 potassium outside, 1 iron and 6 cyanide inside the complex ion square bracket. So you have to calculate what is the oxidation number of iron there. So 4 potassium is 4 times plus 1, because everybody knows that potassium has a charge of plus 1. And in the square bracket is X, because your iron, you don't know what is that oxidation state of iron. And cyanide, what is the charge of cyanide ion? It is a charge of -1. Yep. X is for iron, 6 cyanide is 6 times -1, and the whole molecule, the whole coordination compound of D has a 0 charge. You don't see any charges here. So X is equal to, so 4 plus 1 plus X minus 6. So X is equal to 2 plus. So your ion carries with it 2 plus charge, which is bonded to 6 minus. So this complex ion has a charge of 4 minus, yep, which is neutralized by 4 potassium ion counter ion. So that is how you calculate the oxidation state of the transition metals in coordination compounds. Yep, I hope that is clear. So you can go through the sentences, yeah, here. Each nitrate ion for B, each nitrate ion has a charge of -1. Therefore, the cation, the complex ion, this is the cation, must be CrNH6 3 plus. NH3 is neutral, so the oxidation number of chromium is 3 plus. C, because the CO species are neutral, the oxidation number of iron is 0. Because your carbon monoxide is a neutral molecule, doesn't carry with it any charge, and the whole thing doesn't have any charge, so your iron is 0. And lastly, for D, I'm repeating, each potassium ion has a charge of +1, therefore the anion has a charge of -4. Next, we know that each cyanide group bears a charge of -1, so iron must have oxidation state of +2, like we work it out in these white boxes. Yep. So you can do a practice exercise for this. Can you try and work out what is the oxidation state of AU there? Can do this together. So there is only one potassium outside of the square bracket. So that's +1, plus X is the oxidation state um, of gold, which you don't know. Hydroxide has a charge of -1, and there are 4 of them. So +1 plus X minus 1 is equal to 0, because the whole thing is already neutralized through the action of this counter ion and that complex ion. So X is equal to +3. So the oxidation state of gold in this coordination compound is gold 3+. Yep, I hope that is clear to you. Next, I would like to go through how you would name coordination compounds. There are 6 rules that you would follow when you are naming coordination compounds. You would already know various types of ligands, and you already know how to calculate the oxidation number of the metal. Those are 2 very important things that you should sort out before you can start naming coordination compounds. So when you are ready, you can then start the process of naming the coordination compounds. Now, the cation is named before anion, as in other ionic compound. If you can recall sodium chloride, NaCl, we call it sodium chloride. We don't call it chloride sodium. We always name cations before anion. So that is the first rule. So if your cation is a complex ion, so you name that complex ion first, and then you name the counter ion, which is the anion. Yeah. The rule of naming cations before anion holds regardless of whether the complex ion bears a net positive or a net negative charge. For example, in the K3FeCN6 and CONH4Cl2Cl compound, we name the potassium first in this example. We name the potassium first. And then, but in this example here, we name the complex ion first because those are the cations. Yep, that is first rule. Now, second rule, within a complex ion, the ligands are named first in alphabetical order, and the metal ion is named last. And there is no space. There is no space in the name of the complex ion. Yeah. So if you have, for example, this complex ion here, it has 1 cobalt, 4 ammonia, 2 chloride. You would name the ligands first. And if you have 2 ligands like this, you have amine and chloride. A comes before C. So it's amine first, and then chloro, and then cobalt. We will go through this later. After you finish with the cation, then you say chloride. Yep, don't worry. Rule number 3. The names of an ionic ligand must end with the letter O. For example, chloride, you call it chloro. Bromide, you call it bromo. Iodide, you call it iodo. Cyanide, cyano. Hydride calls hydrido. Yeah? So any ligand which is negatively charged, you put O at the end of the name. Whereas neutral ligand is usually called by the name of the molecule. So but there are exceptions. The exceptions are when you have water, you call it aqua. When you have carbon monoxide, you call it carbonyl. When you have ammonia, you call that ligand amine. Amine with double M. So we have a list of common ligands shown in here. Yep. Your bromide is bromo, chloride is chloro, cyanide is cyano, hydroxide is hydroxo, oxide is oxo, carbonate carbonato, not carbonara. Nitrite is nitro, oxalate is oxalato. Yeah. Ammonia is amine, carbon monoxide is carbonyl, water is aqua, ethylenediamine is ethylenediamine, ethylenediamine tetraacetate is ethylenediamine tetraacetato. You have to put acetato because this has a negatively charged ion. Yeah, EDTA is a negatively charged ion like you saw in the beginning of this lecture. So it's not a tetraacetate, it is tetraacetato. Okay. Okay, that is rule number 3. Rule number 4. When several ligands of a particular kind are present, we use the prefixes di, tri, tetra, penta, hexa. If you have 2 waters, you say diaqua. If you have 3 ammonia, so you say triamine. Yeah. If you have 3 chloride, so you say trichloro. 4 chloride, you say tetrachloro. Yeah. Thus, the ligands in the cation, like here, are, you have amine, chloro, and cobalt. So it is tetraamine, yeah, tetraamine dichloro. Why do we name amine first? Because amine starts with A and chloro starts with C. You do not put into account this bilangan, tetra or di or tri, yeah? You only look at the name, the actual name of the ligand. So amine comes before chloro. Note that the prefixes are ignored when alphabetizing the ligands. If the ligand itself contains a Greek prefix, for example, ethylenediamine, yeah, ethylenediamine, you already have di in there. So you use the prefixes bis, tris, tetrakis for 4, yeah, bis for 2, tris for 3, tetrakis for 4 to indicate the number of ligands present. So if you have the example that we went through earlier, this one, then you say that this is a tris ethylenediamine nickel chloride. Yeah, tris ethylenediamine nickel chloride. This is tris oxalato. Why we don't say tris ethylenediamino? Because ethylenediamine doesn't carry a charge. But oxalate carries a charge, so it is oxalato. So tris oxalato, iron 3. So it's potassium tris oxalato iron 3. You name the potassium first because potassium is the cation, whereas this thing here is the anion. Okay, that's rule number 4. Rule number 4. Right? And rule number 5. The oxidation number of the metal is written in Roman numerals following the name of the metal. For example, the Roman numeral 3 is used to indicate the +3 oxidation state of chromium in this here. So we call this, what do we have here? We have chromium, we have ammonia, 4 of them, and we have chloride, 2 of them. So we say, for the 4 ammonia, we say tetraamine. Remember, there shouldn't be any space within the cation or within the same anion. There shouldn't be any space. So tetraamine, 2 chloride is dichloro. Tetraamine dichloro, no space. And your chromium is chromium 3. How do you know it is chromium 3? It's really very simple. Oops, let's try and calculate the oxidation state of your chromium there. So we have a complex ion. You don't know what is the oxidation state of chromium. So 4 times 0, 4 ammonia plus 2 times minus 1 for 2 chloro, and the whole thing has a charge of plus 1 equals to 1. So x plus 4 times 0 plus 2 times minus 1 is equal to 1. So x is equal to plus 3. Right? So it's chromium 3. So the name of this complex ion, which happens to be a cation, is called tetraamine dichlorochromium 3. No space. Yep. And then, if the complex ion is anion, or if the complex ion has a negative charge, then the name of the metal center ends in ate. For example, the example here is you have potassium as a counter ion, which is the cation, and you have FeCN6. You have 6 cyano. So hexacyano, what is the oxidation state of iron here? We went through it there. It is 2 plus. Yeah. Hexacyanoferrate 2. Yeah. It is still. I'm going through this very, very slowly with you, so you can follow it easily. We have, let's try and calculate the oxidation state of iron in this case. So x plus 6 minus 1, 6 minus 1, this is x, this is 6 minus 1 is equal to 4. So your x is equal to plus 2. Yep, x is equal to plus 2. So it is called hexacyanoferrate 2. But why not ferrum? Why not iron? Because this is minus 4 minus. I'm sorry. 4 minus. Yep. Please correct my notes if this is a lot of mistakes here. 4 minus. So x is plus 2. So hexacyanoferrate 2, because iron, yep, iron, if it is in anionic complex, is called ferrate. Yeah, ferrate. So it's, this whole thing is called potassium. Yep, you have, so the whole thing is potassium. The coordination compound is called potassium hexacyanoferrate. Now, please note that there is a space between the cation potassium and the anion hexacyanoferrate. So this thing that I make it into red now has a name of potassium hexacyanoferrate. Yep. Potassium space, Y space, because we are moving from a cation to anion. There must be a space, just like you put sodium chloride. There is a space between sodium and chloride. So potassium space, hexacyanoferrate, no space. Why no space? Because it is in the same ion. Yeah, it's in the same ion, hexacyanoferrate too. Right. So note that the Roman numeral 2, you use 2 Roman numeral here, indicates the oxidation state of ion. So the table below gives the names of anions containing metal ions. So if it is aluminum, if aluminum is in the complex ion negatively charged, it is called aluminate. Chromium is chromate. Cobalt is cobaltate. Copper is cuprate. Gold is aurate. Iron is ferrate. It's not ironate. It's ferrate. Lead is plumbate. Manganese is manganate. Molybdenum, molybdate. Nickel, nickelate. Silver, argentate. Tin, stannate. Tungsten, tungstate. Zinc, and becomes zincate if they are in the negatively charged complex ion. So I hope that is clear. So I'm going to let you go through example 22.2, which is in your notes. Please go through this, and I'm going to give you a few exercises, through the Telegram group. So your assignment is go through your notes, read example 22.2, which I took from, I think, Chang textbook. You try to understand everything. Example A, B, C, D, and also an additional question here, your practice exercise. Similarly, you can also please go through example 22.3, which you convert from name to formula. Convert name into formula. So those are your assignments, and I'm going to go through the structure of coordination compounds later in the next lecture. So that concludes my lecture number 12. I think this is lecture number 12, and I hope you understand everything that I have explained in this video. Go through example 22.2 and 22.3 yourself, and I'm going to give you a few practice exercises later. So that's it. Thank you very much. Have a good, I don't know, this is a weekend. Have a good weekend, everyone. If you happen to watch this during a weekday, so have a good weekday. So bye, take care, and keep safe. Assalamu alaikum.